Imagine asking an AI a simple question inside a company. Ask something like, who's responsible for the system that processes customer billing? The AI searches thousands of documents and returns something that looks helpful. It mentions the building platform, it'll mention maybe a team name, but it never clearly answers the question fully. Why? Well, because the answer was never inside a single document. The real answer depends on relationships. Which system handles billing? Which team owns that system? Which manager leads that team? And which product the system supports? Traditional Retrieval Augmented Generation, or RAG, is excellent at finding documents that look similar to your question. But it struggles when answers depend on how things are connected. This is exactly the problem that Graph RAG architecture is designed to solve. In this video, we're going to walk through what Graph RAG is, why traditional RAG starts to break down in complex environments, and how graph-based architectures allow AI systems to reason across relationships instead of isolated pieces of text. Okay, so before we talk about graph RAG, let's quickly review how traditional RAG works. RAG combines two major components. First, the retrieval system that searches a knowledge base or something like that. Second, a large language model that generates an answer using the retrieved information as context for that answer. Most modern RAG systems follow a similar process. Documents are broken into smaller pieces called chunks. Each chunk is converted into a vector embedding that captures its semantic meaning. When a user asks a question, that question is also converted into an embedding. A vector database then finds the chunks that are most semantically familiar or similar to the query that we've asked. Those chunks are then passed into the language model, which generates the final answer. Now, this approach works extremely well for many problems. It is fast, scalable, and relatively easy to implement. But it assumes something very important. It assumes that similar text equals relevant knowledge. And in many real-world systems, that assumption does not always hold true. Traditional RAG works best when answers live inside an individual document. For example, what is the refund policy? How does a specific product work? What are the steps for submitting an expense report? How many vacation days do I have left? In these cases, the answer is usually contained within a single document, article, or system. But enterprise knowledge often works differently. Real organizational knowledge is connected. So when we think about questions like these, for say, which system processes customer data? Which vendor supplies components for product X? Which department owns the data pipeline that feeds our analytics platform? These questions often require multiple steps of reasoning. The AI must identify entities, understand the relationships, and follow chains of connections. Vector search alone does not understand these relationships. It simply retrieves chunks of text that look similar to the question that we're asking. This can lead to several problems. First, it causes incomplete answers when the necessary relationships are spread across multiple sources. Second, we get these hallucinations that everybody's familiar with, And this is because the model is trying to guess at what the missing connection is. Third, we have difficulty answering multi-hop questions that require reasoning across several entities. So now, to solve this problem, we need a way for AI systems to understand not just information, but how information is connected. This is where GraphRag architectures become powerful. GraphRag extends the traditional RAG architecture by introducing a knowledge graph layer. So instead of representing knowledge only as text documents, GraphRag models will hold information as entities and relationships. In a graph model, entities become nodes. And when we think about what a node is or an entity, right? We talk about things like customers or what system we're using or different employees, products, policies, those types of things. Then we have relationships between those entities and they become edges. So if we think about a team that owns a system, a product depends on a supplier. A data set feeds into a machine learning model. Once these entities and relationships are represented in a graph, AI systems can retrieve knowledge not just by similarity, but by following all of these connections as they're related. What this does is it allows the system to answer questions that require multiple steps of reasoning. So now, instead of retrieving a few isolated text chunks, GraphRag allows us to retrieve connected pieces of knowledge that form a meaningful context. That context is then passed into the language model, which generates our grounded answer. So if we break this down simply, GraphRag allows the AI to understand structure, not just language. A typical GraphRag system includes several key components. First is data ingestion and knowledge extraction. We get information from documents, databases, and structured systems and analyze them to identify the entities and the relationships. These elements are used to build a knowledge graph. Second is the graph storage layer, usually implemented with a graph database. Graph databases are optimized for traversing relationships from one entity to another, from one node to another, which makes them ideal for this type of architecture. Traditional relational databases don't prioritize the relationships as they are defined with joins to retrieve the information. When we use a graph database, those relationships are prioritized as part of the overall structure of the database and the data model. The next is the retrieval orchestration layer. So when a user asks a question, the system analyzes the query to determine which entities might be involved. The system may perform graph traversals, vector searches, or a combination of the two to get the right answer. This process retrieves relevant nodes, relationships, and supporting text. Fourth is the context assembly. Now, instead of simply returning text chunks, the system gathers connected entities and relationship paths. This provides the language model with a richer understanding of the problem. Finally, the language model generates the response using this structured context. Now, because the retrieved information reflects real relationships in the data, the model is much less likely to hallucinate and much more likely to produce accurate explanations. It helps to think about the difference between these approaches in terms of what they retrieve. So traditional RAG retrieves documents that look similar to the question we're asking. GraphRag retrieves entities and relationships that are relevant to the question. Traditional RAG is excellent for document search, things like FAQs and knowledge bases. GraphRag is especially powerful for problems involving things like system dependencies, data lineage, organizational relationships, root cause analysis, complete reasoning across multiple sources, and more. In practice, many organizations combine these approaches. Vector search provides broad semantic recall. Graph retrieval provides that structured reasoning and context. Together, they create a far more reliable AI system. So, when we think about the next generations of enterprise AI, it's not going to be built on documents alone. It will be built on connected knowledge. Organizations do not operate as collections of isolated text. They operate as networks of people, systems, data, and decisions. GraphRag allows AI to navigate those networks. So instead of asking an AI to guess the answer from similar documents, we allow it to follow the actual relationships that define how the organization works. And when AI can understand those connections, it moves one step closer to reasoning about the real world. That is the promise of GraphRag. Hopefully this video gave you a good breakdown of the difference between traditional RAG and GraphRag, and hopefully you enjoy this content. Look forward to my next video, which will do a comparison of world models and large language models. Thanks a lot. Have a great day.